All right, you little dingbats, this is our last stretch of time, so I threw together two quick videos just so we don't have to use stuff entirely off of YouTube. We've done moles, we've done reactions, we've combined them, and you guys are great at stoichiometry. Normally our last 3 weeks of school is spent doing acids and bases. We're just going to do two lessons, a lot of real-life applications of acids and bases that we normally go through, but we just want to give you the foundation of it in case you're going to see it later in science classes. So the two lessons are really going to break down into understanding general characteristics of what acids and bases are and how to calculate pH and how it affects those two things. And then your lesson for Tuesday, Wednesday, Thursday will have to do with titration equations and how to take a neutralization reaction and calculate different volumes that we'd need. Normally we do about a 4-day lab with the titration. So let's start with just acids and bases in general. There's lots of real life information that we can cover, but when we talk about acids, a lot of times you'll hear the word acidic used. I mean, anything that's acidic is an acid. It's not just the crazy stuff from the movies you hear about. We know from our naming chapters that acids almost always start with H, and we'll get more specific than that, but we know H2SO4 and HCl and HNO3 are all examples. Normally we recap a little bit about adic and when to use hydro. Anytime we have a polyatomic ion, we want to look at the ending. So this would be sulfuric acid. Since this is a binary acid, H in just one thing, we use hydro. So this is hydrochloric acid. And then again, here's nitrate, and H becomes ic, so this is nitric acid. To clarify, when we break these down though, when they're in a solution of water and they're aqueous, it's not an H, it's really a hydrogen ion. This is two hydrogen ions with a sulfate ion. This is one hydrogen ion with a chloride ion, and that's something we talk a lot about. And this is what we call a monoprotic acid because there's only one H, and this is a diprotic acid because there's two hydrogen ions. And that's really what makes acids acidic. It's all those H pluses floating around. This is what has to do with stomach acid. When you have lactic acid build up in your muscles, it's a bunch of these hydrogen ions building up. So digging in a little bit here, this is going to be pretty short and sweet, and you'll look a little bit more about these online, but general characteristics of most acids is that they're electrolytes, which means when they're in a water-based aqueous solution, they conduct electricity, and that's because they get pulled apart and there's those separate ions. Normally acids are associated with a sour taste. Things like lemons and oranges all have citric acid, and that's that sour taste. Vinegar is actually a solution of acetic acid, and not that you want to taste vinegar, but sour is definitely how we describe that. A lot of sour-based candies have acidic components to it, and even your stomach acid is just basic hydrochloric acid, which is why when you burp up sometimes, it's that really, really gross taste. That's that sour acid taste you're tasting there. Normally we do a big lab about you drop some zinc in, and one of the properties of acids is that most acids will react with metals, and you can see in this single replacement reaction here what they're going to form is hydrogen gas, and that's this left all by itself after that single replacement reaction. That's a really important characteristic of a lot of acids, and that hydrogen left by itself is usually a buildup of pressure, and in our lab we see how combustible it is, and it's a lot like the Hindenburg blimp, and that was a huge part of history. Lastly, just general terms, we say that acids react with bases, and when acids react with bases, this will be really tomorrow's lesson, but they always produce salt and water, and we'll dig into that a little bit more. On the flip side, when we talk about bases, usually we use the word basic, and this doesn't mean we're walking down the hall with Starbucks and Ugg boots. Basic means it's a solution that's considered a base. So again, this is a very, very general characteristic, but bases usually end in OH, and we recognize that that's hydroxide. So you'll see these are two great examples of a base. We have sodium hydroxide and calcium hydroxide, and these are basic components. These are basic solutions. Not all bases end in OH. For example, ammonia here, we would normally learn in class, there's some different definitions that make things a base, but ammonia is a base, but the ones you guys use will usually be hydroxides present. Okay, so again, hydroxides are one of the main characteristics, not the only one, but anytime it's a hydroxide, there's a lot of OHs in solution. That is something that's very, very basic. And when we put these in water, we know that they also get pulled apart, which we see right here. When we put sodium hydroxide, there's really a bunch of sodiums floating around, and there's a bunch of hydroxides floating around, so it's going to conduct electricity again. Usually with bases, we say that they have a bitter taste. So even, I don't know if you guys ever got your mouth washed out with soap, but soap is something that we kind of associate with how bases would taste. Usually they're very, very slippery, again, like soap. If you spill sodium hydroxide on your hands are very, very slippery. And a lot of times these are used in cleaning products, and that pungent smell you have with ammonia and bleach, a lot of times that's evidence of a base. Bases do not react with metals the way that acids do. That has to do with the whole single replacement reaction. And again, this should look familiar, but bases will react with acids to produce salt and water. We really want to keep that in mind as we go into our next day's lesson. So, with that being said, those are characteristics you need to know, but we also want to bring some numbers into play when we explore this. So, we have a numeric system for how we decide if something's an acid or a base, because a lot of times we don't want to taste it. And what that's called, you probably have heard of this, but it's called the pH scale. And I'm really going to simplify it here, but the pH scale has to do with logarithmic and powers of 10. It's a logarithmic scale. What that means is we're dealing with really, really, really small changes on a molecular scale, but we want to reflect that in normal sized numbers. And if you've ever worked with logs in math, it really helps us relate those number changes to something more understandable. So what pH really stands for is the power of hydrogen. You can kind of think about, we know hydrogens have a lot to do with acids and bases like we talked about. So just to kind of put this in perspective here, the pH scale goes from 0 to 14. Okay, I'm sure you guys have maybe seen this in middle school before. But right in the middle at 7 is pure water. And pure water is not acidic, it's not basic, it's neutral. Okay, so that's what we're always going to kind of think through. If there's a lot of hydrogens present, that means something's going to be an acid, and it is an inverse log proportion. So what that will do, if there's a lot of hydrogens, it'll give us a low number. You can see things like our stomach acid, lemon juice. A lot of these things right here are acidic, and we'll talk about the relationship here, but if you look down here, if it's less than 7, what that means is there's a lot of hydrogens, and since it's the inverse log, it will give us a low pH. So anytime a pH is less than 7, it's acidic. On the flip side, if there's a low number of hydrogens, that would mean we have a lot of hydroxides. We call that basic. So all of these pHs bigger than 7, you see cleaning products, certain alkali metals, there's that soap again, baking soda as a base. Anytime we have a pH greater than 7, it's going to be basic in nature. And if it's 7.00, that means the hydrogens and hydroxides, and if you look, guys, H and OH is water. It's just a different way for us to write H2O. And if they're equal, it's not acidic or basic. It's right in the middle and it's neutral. We're going to do 2 practice problems, and this is what your homework and quizzes will look like. The way that we calculate pH is the inverse log. That's a negative sign, so the inverse log. And since it's the power of hydrogen, we take the inverse log of the hydrogen concentration. So a nice easy example to start off with is, what is the pH of a solution of vinegar, which is an acid, keep that in mind, if we know the hydrogen concentration is 0.00235 molar. Usually we're going to be working with small numbers here because it's on the molecular scale. We're not talking about very much here. So what we're always going to do is we're going to start off with our blank equation. I want to find the pH. pH is the inverse log of hydrogen. That's my equation. And I know my hydrogen since they gave it to me in the problem. So I go plug my hydrogen in, which means the pH is going to be the inverse log. So on your calculators, you'll type in negative log of 0.00235 molar. pH is just a number scale. There's no units. So that comes out to 1.63. And if I go back, everybody, 1.63 is right over here, which is acidic, which is what I put right here, which makes a lot of sense. If the pH is less than 7, it's acidic, and vinegar is acetic acid. So that fits perfectly and makes sense. But pH is the inverse log of hydrogen. This is an example of the harder types of problems. So on this one, we can't just rock and roll and do pH because sometimes it's going to give us the hydroxide concentration. So there are 2 ways to do this. You guys can kind of see the 2. But what this one is saying is, what is the pH of a solution of potassium hydroxide? Hydroxides are bases. If the hydroxide concentration is 6.50 times 10 to the negative 3rd molar. Okay? So the first way, and I'm really going to go kind of quick here, but you guys will get the hang of it. There is a thing called pH, which is the power of hydrogen. There's also something called pOH, which is the power of hydroxide. And it's found using the same way. So if I go find the negative log or the inverse log of my hydroxide, that will give me my pOH. Now that's not what we're familiar with our scale. There is a relationship though, because of the way that water dissociates. pH plus pOH, they kind of work as an inverse relationship. Those two things always will add up to 14. So if I go plug in the fact that I know my pOH is 2.19, I can subtract over and figure out that my pH would be 11.8, which is greater than 7, which means it's basic, which makes sense for my hydroxide. So this is method number 1, going through pOH. You guys might see another YouTube video about this. The other way has a little bit different numbers. You can see right here, this is another constant equation we'll use. We know because of the way that water dissociates, there's always a direct relationship, an inverse relationship. If I have a lot of hydrogens, I don't have very many hydroxides, and vice versa. You can see again, here's this 14 here, and this is bringing that whole idea of the log scale back into play. But this is a constant equation you can always use. And if I look here, I know my hydroxide, so I can go plug that in. Then I would divide over to solve for my hydrogen. Again, I'm going fast, but on your calculator, make sure you're careful with parentheses here. If I divide that out, what that gives me is my hydrogen concentration. That's a really, really tiny number, so it should give me a big pH. And I know now if I have my hydrogen, I can find the power of my hydrogen using my pH one. If I take the, oops, I forgot the negative sign there. If I take the inverse log of this, it still gives me 11.81, which is exactly what I got over here. Two different ways to do it, but remember, if the pH is less than 7, it's acidic. If the pH is more than 7, it's basic. If the pH is 7, it's neutral. You know those characteristics, and this is a numerical way to think about it. So get after those problems, ask if you have questions.